Hello, friends. I've been quite busy with projects that do not center around my 1802 universe. Over the past year, I've made some upgrades to my system. I felt that it was time to show the world what I've done. The cameras of today run so fast that they do a poor service to the 7-segment display these retro-style systems utilize. Please excuse the appearance of non-functioning digits. I've increased the available system memory. The prior system had 256 kilobytes of RAM. This new system has 1 megabyte of RAM. I've also added a socket for an optional 64 kilobytes of read-only memory once I have a stable OS to use. With 16 banks of 64 kilobytes to address, I needed to add some additional address lines to my memory manager unit design. This unit now controls address lines A16 to A19. You may have noticed a small jumper wire at the bottom. I had to make a slight modification to the unit to handle another board I'll show later. I'm finding ways to utilize all of this memory at a slow pace. I've already created my OS that has code in Bank 0. The storage it uses for basic OS and DOS operations resides in the next bank. I wrote a text editor whose code resides in Bank 2. The text is stored in Bank 4, and the index to the text is stored in Bank 3. I sometimes interchange the term bank with page. My initial design was for the OS to provide utility services that other programs can use. The editor makes use of these services by calling routines in Bank 0 of memory. The latest board I've created is what I call my logic analyzer. I've got a number of logic analyzers, including an HP 1670G, but the setup I need requires this design. The logic analyzer is very simple. A Nano Every controls it. You'll see that I've moved my system's 4 MHz clock signal from the CPU board to this board. Both boards have a socket for the oscillator, so I can always move it back to the CPU should I choose to do so later. The board circuitry allows the Nano to select between a 4 MHz clock, which is the default upon power up, or the Nano can generate a logical clock signal. There are a total of 6 574 octal flip-flops, which the Nano can order to capture a large number of signal states. One by one, the Nano can then instruct a single 574 to expose its values to an internal bus. A 299 universal shift register then performs a parallel load of the signals, and then the Nano sips at the byte 1 bit at a time. I've gotten better at writing applications using Visual Studio and C#. I wrote an application which runs on my Windows desktop. It interfaces to the Logic Analyzer Nano via a USB COM port. On the right is my listing display. By selecting a page value in the upper right and clicking the Load Listing button, I can import an A18 assembler listing file. The application parses the listing file, creating an internal list indexed by memory location. I can set breakpoints at selected addresses, and in this picture you will see 2 lines highlighted in orange where I set 2 breakpoints. On the upper left are the buttons to control the logical clock. When the logical clock is running, the Nano, the application, has no trouble keeping up with the system. It runs at a much slower pace, but I'm able to capture the telemetry of what the system is doing. This picture doesn't show the telemetry capture in progress. The panel on the left shows the application in playback mode. The playback panel decodes the telemetry that the Nano captured. I'm able to cursor up or down on the telemetry listing with corresponding selection of the address being executed on the right panel. I'm using the Logic Analyzer to reverse engineer RCA Basic 3.1. My goal is to alter it to address an entire bank for program storage and perhaps another bank for variable storage. It is a wild idea for sure, and only time will tell whether I'll be successful or not. Well, friends, that is all I have to share at this time. I may decide to create another video showing the Logic Analyzer in its full glory at a later date. Until then, take care and continue to have fun by being a geek like I am.